Welcome back to The Explainer. Okay, I am absolutely thrilled you're joining me today because we are going on a seriously cool journey. We're going to zoom all the way down from the grand, massive scale of the universe, literally right into the microscopic physics of a single digital pixel. Today, we're unpacking the incredible software and the underlying math that scientists use to simulate the breathtaking images of the upcoming Nancy Grace Roman Space Telescope. We'll be exploring things like the effective point spread function, or ePSF, and this wonderfully quirky electrical phenomenon called interpixel capacitance. I know that sounds super complex right out of the gate, but I promise you, by the end of this explainer, you are going to look at astronomical images in a completely new light.
So let's kick this off with a massive logistical headache. How in the world do you accurately test a space telescope before it ever leaves the ground? The Roman Space Telescope is slated to begin operations in late 2026. It's going to be parked a million miles away, just beaming down terabytes of data. Astronomers really can't afford to wait until it's actually up there to see if their software pipelines work or to figure out how to analyze all that information. They have to prepare right now. And to pull that off, scientists rely on highly complex software simulators to generate synthetic data that mimics exactly what Roman will eventually see.
To really grasp the sheer scale of what we're simulating here, you just have to look at the massive field of view of Roman's wide-field instrument. Roman actually has the exact same 2.4-meter primary mirror as Hubble, but its panoramic field of view, it's literally at least 100 times larger. We're talking about a massive grid of 18 individual detector chips combined to give us a 0.281 square degree active field of view. Simulating something of this magnitude isn't just about drawing dots on a screen. It requires accurately modeling millions of light sources across a vast digital landscape.
But here's the catch. To understand how we simulate that giant view, we actually have to zoom way, way in, down to the microscopic scale of the detector itself. And that brings us to a tiny but honestly kind of troublesome number, 0 to 4%. Now, I know that sounds completely insignificant, but this little percentage is a real headache for engineers. It represents the actual amount of signal leakage happening between neighboring pixels on Roman's detector array. The universe might be sending perfect light to the telescope, but the physical hardware on the spacecraft is, well, wonderfully and frustratingly imperfect.
So what's causing that 0 to 4% leakage? It's caused by something called interpixel capacitance, or IPC for short. Basically, when a digital camera sensor collects light, it's really just gathering photons and converting them into electrical charge inside these microscopic little buckets. Those are your pixels. But because these pixels are crammed so incredibly close together, they start to influence each other electrically. It's kind of like pouring water into a grid of really tightly packed buckets. As one bucket fills up, a little bit of the water, or in this case the electrical charge, just naturally diffuses or overflows into the immediate neighboring buckets. That is interpixel capacitance. It actually slightly blurs the signal before the computer even has a chance to read it. Now, what's really wild is how that tiny bit of signal leakage fundamentally changes the way we see stars. And this brings us to the effective point spread function, or ePSF. You know the standard point spread function, right? That's just the mathematical shape a perfect point of light takes after bouncing through the telescope's optics. But the effective point spread function? That includes the gritty physical reality of the detector grid itself, including that interpixel capacitance we just talked about. When real Roman observations happen, they won't see a perfect, idealized point of light. They'll see this ePSF, and its shape depends heavily on the specific filter being used and the exact microscopic pixel position on the wide-field instrument.
To recreate this beautifully flawed reality here on Earth, astronomers use two main software tools, balancing perfect physics with flawed hardware. First up is STPSF. This is an awesome Python package that simulates the perfect optical paths. It calculates the telescope's mirror aberrations, Fraunhofer diffraction, the whole shebang. But the universe isn't perfect, and hardware definitely isn't perfect. That is exactly where STIPS steps in, the Space Telescope Imaging Product Simulator. STIPS takes those pristine, perfect optical models from STPSF and essentially dirties them up. It injects all the gritty detector flaws, the noise, and the pixel physics. STIPS's entire job is to inject the artifacts that make the simulated image authentically real.
To give you a sense of just how obsessive this gets, STIPS intentionally throws a whole cocktail of imperfections into the simulated scenes. We're talking flat field variations and dark current, which is that annoying false signal detectors generate just from being warm. It adds the leftover scars from cosmic rays zipping right through the sensor. It calculates Poisson noise and readout noise. And get this, it even adds the zodiacal background. That's the ambient glow of dust in our solar system, calculated directly from James Webb models, plus the internal thermal background of the telescope itself. All of this is carefully layered on to make sure scientists aren't practicing their science on unrealistically clean data.
Okay, so how exactly does STIPS actually build these realistically messy stars? Well, it follows a very specific three-step injection pipeline. First, because calculating a totally unique point spread function for every single star would literally take forever, STIPS just extracts a grid of 9 highly detailed, oversampled optical models distributed across the sensor. Step 2, it mathematically convolves those models with a 3x3 interpixel capacitance kernel matrix that basically simulates our leaky water buckets to create the ePSF. And finally, step 3, it projects that ePSF right onto the actual simulated image using mathematical interpolation.
But wait, this brings us to a massive computational roadblock. How in the world does STIPS calculate the exact brightness of every single individual pixel for millions of simulated stars across that giant 18 detector array? I mean, we're talking about a staggering volume of data here. If the software takes too long to calculate how light spreads for just one star, simulating an entire galaxy would take lifetimes. So the software engineers had to get really clever and employ some serious subpixel mathematics. It all comes down to that classic computing trade-off, speed versus accuracy. To map the light onto the pixels, STIPS relies on 2 totally different mathematical methods. You've got bilinear and bicubic interpolation. Bilinear interpolation essentially just looks at the nearest neighbor pixels and draws straight lines between their values. It is super fast and really simple. But then you have bicubic interpolation. This one looks at a much wider grid of pixels to calculate these beautiful, smooth curves. It's highly accurate for sure, but man, is it computationally heavy.
So how do they actually balance this in the code? Well, because the center of a star is intensely bright and incredibly complex, STIPS sets a very strict threshold. The software constantly checks the distance from the center of the simulated star out to the pixel it's working on. If that pixel is further than a distance of 4 from the core, out where the light is faint and mostly uniform, STIPS uses the fast bilinear method. But for those crucial pixels with a distance of 4 or less, right in that intense, complicated heart of the star, the software automatically shifts gears to the heavy, precise Bicubic interpolation.
Now, you might be wondering, why do we care so much about this specific threshold? Well, it is all about the error rates. Using the fast bilinear method out on the outer edges is totally fine. It gives us less than a 1% error, which you'd basically never notice. But if STSS tried to cut corners and use that fast bilinear method inside the dense core of the ePSF, that would jump to a 3% error rate. And in the ultra-precise world of astrophysics, where a fraction of a percent is literally the difference between discovering a new exoplanet or missing it completely, 3% is just completely unacceptable. And honestly, it's worse than just bad math. According to the development literature, applying that simpler bilinear method to the core doesn't just mess up the numbers. It actually produces sharp artifacts near the center of the ePSF. Just imagine zooming in on a simulated star, and instead of a natural smooth peak of light, you see these sharp, jagged, pixelated edges. Those visual artifacts would absolutely wreck the simulated data. Scientists trying to test their delicate galaxy shape measurement algorithms would be completely out of luck. So successfully balancing all this complex math and pixel physics is exactly why the STIPS simulator is such a game changer for the astronomical community. It's completely Python-based and open source, so anyone can get in there and use it. And because it utilizes those clever interpolation tricks we just talked about, it can churn out rapid simulations of Roman's huge field of view. We're talking roughly 20 times faster than the full pixel-by-pixel up-the-ramp simulators out there, like Romanism. It gives astronomers this incredibly efficient, vital tool to rapidly test their science cases and really understand the subtle quirks of those 18 different detector chips before the real data ever starts flowing.
Which leaves us with this final, honestly pretty thrilling thought. Right now, we are pouring an immense amount of human ingenuity into writing software that perfectly mimics microscopic flaws. Leaking pixel buckets, thermal noise, mathematical artifacts. We are mastering the absolute gritty physics of a single digital pixel just to make sure we're prepared.
So if our simulations are this flawless at mimicking the imperfections of our hardware, just imagine for a second what profound, awe-inspiring truths the real Nancy Grace Roman Space Telescope's data is going to reveal about dark energy, exoplanets, and the very fabric of the universe itself. Thanks so much for joining me on The Explainer, and as always, keep looking up.